Great. So I'll start off our meeting. So thank you everybody for joining, and also looking forward to later posting this seminar, since we want to make it available to anybody that's a space enthusiast. We have our own space enthusiast here today. So Dr. Hurd, who actually had a dream of studying rocks from Mars since he was 13 years old. He did his undergrad in geological sciences at Queen's University, and later on continued into a PhD at the University of New Mexico, where he had the opportunity of studying meteorites from Mars. He currently is a professor in the Department of Earth and Atmospheric Sciences at the University of Alberta. And we are lucky to have him today, since he is also a return sample science participating scientist in the Perseverance rover mission. So thank you for joining us here today. Maybe you can give an overview of what you'll be presenting and take it from here. Thanks.
Great. Thanks so much for having me. It's a pleasure to talk to you today. And for those joining later, welcome to you as well. So yeah, I'm going to give you an overview about what this mission, the Mars 2020 Perseverance rover mission run by NASA, is all about. I'm going to give you an almost up to the minute update on what's been going on, but I'm going to give you an overview of how we got to where we are and the capabilities of this fantastic rover, and the overarching goal, which is really to search to see if life ever existed on Mars. We have our rover here. This is one of the first, well, it's not the first, I think it's the second or maybe third selfie that we took with a camera on the end of the arm. And so if you're not familiar with this, it's the camera reaches, the arm is extended out and the camera is pointed back towards the rover, and then a series of images are taken and then it's stitched together to form this. And this is actually where the first two rock samples were collected. That's what the holes are that the rover is looking at on the ground there. And I always like to think the rover's looking rather pleased with itself at this point, having successfully collected the first two rock samples. So you'll see why that's important as I go along. Okay, what's the fundamental question here, though, that we're trying to answer is we're really trying to understand the geology, the geological history. You can often refer to it as the geological evolution of the planet Mars. And really, it has to do with global climate change for the red planet. We know modern Mars looks like what we see on the left there. This is what you might see in a really good telescope. It's a dry, cold desert. There's a very thin atmosphere, 1/100th the pressure of the Earth. It's very cold. There's water ice and carbon dioxide ice in the polar caps, and liquid water is not stable at the surface. 3.5 billion years ago, give or take, it's a different story. And this is on the right is one artist's interpretation of what it might have looked like. There may have been enough liquid water at the surface to have a northern ocean filling the northern lowlands. That's what's shown there. Certainly, it appears there was a thicker atmosphere, so you can see that sort of depicted by the clouds, etc. So the point is that it was more warmer and wetter. I think that's generally agreed. How much warmer, how much wetter is kind of continued to be debated among planetary scientists, but it's generally agreed that based on the rock record that we see from previous missions in particular, we see that this is what Mars might have looked like. But then the fundamental question is, why did it go from that, what we see on the right here, to what we see here today on the left, where there's no liquid water on the surface and the surface is bombarded by radiation and definitely not hospitable for life. And that then, of course, goes hand in hand with, okay, there used to be liquid water. Did Mars ever have life? And the time frame that we're talking about is it's useful to sort of compare it to the Earth's rock record. And this is in one sweeping image, kind of a summary of what we know about life on Earth. But the first sort of familiar fossils show up about 500 million years ago or so. The first multicellular organisms not too long before that. And but what we're talking about here, time frame that we're talking about for Mars climate change, or when we think that it started to go from warmer and wetter to dried out, is way back here at about 3.5 billion years ago. And what was happening on the Earth at that time? Well, we had photosynthesis, we had bacteria, we had single-celled organisms. So really what we're looking for, if we're going to send a rover to Mars, is not what we see in the left, classic fossils. What we're really looking for is going to be a lot more subtle than that. It's going to probably be microbial, and maybe we're not even looking for fossilized microbes, but the effects of those microbes doing their metabolism in the substrate, in the sediment, like what you see here on the right. This is what's known as a stromatolite. This is the effect of bacteria moving and growing and living within within layers, sediments actively living in sediments in the ocean, or in the tidal zone typically, and doing photosynthesis in that environment, and building up layers as the sediments kind of sort of flood there, or fill up, or cover them up, to sort of grow up through them. So we might see that. We might not even see that. We might see chemical, what are called biosignatures, indicators that life was there. So if that's the type of thing we're looking for, then what do we need to do to actually test this, whether life ever existed in ancient rocks on Mars? The 4 main goals of the mission of the Mars 2020 Perseverance rover mission are as follows. The geology, which underpins everything. It's the context for everything. It's going to give us an idea of what happened when and what the environments were. The second thing is the astrobiology. It's this really intriguing study of life outside the Earth, which we've never demonstrated before. The third part is sample caching, for reasons that you'll see, but it has to do with what are the criteria that we need to meet to actually determine whether life was ever there in the samples that we collect, and in the environments we investigate with the rover. And then the fourth part is preparing for humans to explore, to eventually explore, live on Mars, at least temporarily. So how do we do that? We send a very, very capable rover. Here it is schematically with the instruments. And so you can see this is about the size of a small SUV. And the mast here is about 2.5 meters tall. And at the top of the mast, we have a set of panoramic cameras called Mastcam Z, which can zoom up. We can see details 3 kilometers away. We have the laser micro imager called SuperCam, which is actually really cool because it zaps rocks up to 7 meters away with a laser and then produces a plasma. And then a telescope looks at that plasma as it's being produced, analyzes the signal coming from it, and tells you what elements and materials are, what the rock's made out of. The telescope can also be used for long distance observations. On the mast, we have META, which is a weather station that provides information about things like obviously like temperature and relative humidity, wind sensors, that sort of thing. In the body of the rover, we have RIMFAX. This is subsurface radar. We can penetrate up to something like 10 meters or so, depending on the materials, and see layers with a resolution of about 10 centimeters. And then on the end of the arm, we have the cylindrical thing I'll come back to. That's the sampling coring device. But then we have Pixel, it's an X-ray spectrometer, and Sherlock, which is an ultraviolet spectrometer, and a camera that goes along with it called Watson. That's the one that took the selfie on the first page there. Then we also have MOXIE, and MOXIE produces oxygen from Martian carbon dioxide, from carbon dioxide in the Martian atmosphere. The atmosphere is like 96% carbon dioxide. And this is a technology demonstration that relates to that fourth goal that I mentioned about humans exploring Mars. So it did successfully run. This was from the first test that was done in April, and it produced almost 6 grams of oxygen in about an hour, which I think I was told is enough to keep an astronaut alive for about 6 minutes, something like that. But the point is that you would actually, what you would do, the whole idea is about this is basically, it's splitting off oxygen from carbon dioxide. And what you would do is you would perhaps scale up this type of thing to, orders of magnitude more, send it to Mars, let it sit on the surface and produce oxygen from the Martian atmosphere, which could be used to support humans going there, both for breathing as well as for an oxidant for fuel. So I'm not going to talk too much more about that, although it's quite an interesting technology demonstration. The other technology demonstration that's not shown here is Ingenuity. And Ingenuity is a small helicopter that we delivered to the surface early in the mission. You can see it here. It was strapped to the belly of the rover, and you can see it in the sequence being lowered down and the legs coming down, and then us driving away. This was the first selfie that we took to show perseverance with our little buddy that we dropped on the surface, Ingenuity. Ingenuity looks like this. It is it operates by solar charged batteries that power dual counter-rotating rotors. And the interesting problem is how to demonstrate powered flight on another planet, or how to do it in the first place. And the way you do it is you have to take into account several things, including lower gravity, 1/3 the gravity on the surface of Mars. So that means there's less lift that you need to lift something off the ground. This weighs 1.8 kilograms on the Earth. The other thing, though, is the atmosphere is 1/100th the pressure of the Earth's atmosphere. So you need to, that's a counter factor. So you need to actually have blades that rotate faster than they would normally in Earth's atmosphere. And in this case, it's 2,400 RPM for these counter rotating blades. And it's been very successful, and I'll come back to some of how it's gone from a technology demonstration to doing other things for us now. We have lots of cameras as well. And so in addition to the science cameras that I mentioned, we have engineering cameras, including NavCam up here, and HazCams, the hazard cameras on the front and the back. These are full color, quite high resolution imagers. And together they allow us to do things like autonomously rove across the surface with software on board that analyzes whether a particular rock is too high or a dune is too slippy potentially for it to rove. And so there's lots and lots of cameras, and there are also cameras on the entry, descent, and landing. But let's go back and talk about the history of this and the timeline. The landing site, which I'll come back to, I'll talk about in more detail, Jezero Crater, was selected in November 2018 at a community workshop. I was fortunate enough to go and attend. And the rover had been designed, it was being built at the time, and then it was launched on July 30th of 2020 at about 10 to 7 in the morning, my time here in Alberta. And we couldn't gather together because of COVID, but we had to live vicariously through others, including through this photo taken about 5,000 feet over Cocoa Beach at the time of the launch. It must have been absolutely phenomenal to be witnessing it like that. But there it took off, headed to Mars. It spent the next 6 months and 20 days cruising to Mars, covering 471 million kilometers, and then landed on Mars on February 18th at about 10 to 2 Mountain Time. And we've been successfully on surface operations ever since. But it is worth noting the entry, descent, and landing. At the time when we landed, the one-way travel time for a signal from Mars or vice versa was over 11 minutes. And so it's important, and this continues to be the case. So there's we're not driving, nobody's real-time driving this rover with a joystick. And certainly that was not the case during entry, descent, and landing. So everything that is shown in this schematic diagram was done autonomously. And it took about 7 minutes from the cruise stage separation, where it was going, I think, something like 10 kilometers per second still at the top of the atmosphere, to gently set down on the surface is about 7 minutes. That's why it's called the 7 minutes of terror. And of course, as you're watching the signal come back, like many of us did, everything's happened actually 11 minutes before. So you don't actually know until the signal reaches you. but I'll go through this and you know, suffice to say it worked beautifully, but there's some really amazing technology here that also does relate to sending humans to Mars eventually as well, because this is testing advanced landing systems. So it separated from the cruise stage and then it entered the atmosphere. And of course you get heating at the top of the atmosphere by friction against the heat shield. And then it got slowed down enough so that the hypersonic specially designed parachute could open. And at that point, the heat shield separated, and then it got a radar lock on the surface. The radar on board was able to lock onto the surface to get the altitude. And then what's really cool is that it had onboard in the onboard computer, it had maps that it used to compare what it was looking at the surface to identify features and register those features against the maps. So basically knew where it was in against the backdrop. And it also knew in those maps, it knew that there were certain areas that you shouldn't land in because it's too rocky or too many dunes, that sort of thing, too dangerous. So there were sort of zones that were okay and other zones that were not. So it got a terrain relative navigation solution at this stage. Then the back shell separated, and then the jetpack, as I call it, the descent stage fired with 4 rockets that then lowered it to the surface. Now it's at this stage during the powered descent that it did a divert maneuver, and that meant it diverted laterally away from an area that it was going to land in that was a no-go zone based on those onboard maps and its terrain relative navigation solution. So this is all happening. This is amazing, right? This is all happening completely autonomously. And then it did the sky crane maneuver, which has been done before, but this is kind of amazing that it slows down and then it lowers this multi-billion-dollar spacecraft, this rover, down on 3 tethers to the surface. And then when it touches down, the tethers separate, and then the descent stage flies away and crashes. So from 10 kilometers per second to gently down on the surface in 7 minutes, and really amazing. There is a video. If you haven't seen it, I can provide the link, but it's on YouTube. You can probably just even Google JPL Perseverance landing. But it's a narration of this as the signal coming back, superimposed on images and video from the landing, because we had on board cameras looking up, looking down. They're basically GoPros that were modified for space flight, kind of almost at the last minute, on different parts, including on the descent stage, on the deck looking up, the descent stage looking down. So there's all kinds of really rich information that could be seen that documented this whole process. But the first thing that was received about 40 seconds after touchdown was confirmed is this image here, which is it looks like it's black and white, but it's basically from one channel in one of the hazard cameras looking through the lens cap, which was used to protect the lenses from all the dust that got kicked up by the landing. So this confirmed it's, you know, the horizon's in the right orientation at this stage, and you also see the shadow of the parts of the rover on the surface, and even some rocks and soil around. And then also really cool, about 10 to 20 seconds after that, this image was sent back, and this plume that you see here shown by the arrow is the descent stage crashing about 600 meters away. So it actually caught the explosion of the descent stage, sacrificing itself after having done a great job delivering the rover to the surface. And then the next few days and actually weeks were all about checking out the different instruments, the capabilities of the rover, making sure everything was working well, including standing up the mast. This is on Sol 3. Sol is a Martian day, so this is on the 3rd day that we were there. And you can see some dust on the deck there. You can actually see, so this is a panorama of the landing site. You can see where the descent stage engines have blown dust away, revealing some rocks underneath and obliterating part of this dune right here. And you can see off into the distance, and we could see these hills in the far distance are the rim of Jezero crater that we're in. So we are in this crater. It's a crater that is on the northwest corner of the Isidis Impact Basin. Which is itself a major basin that's about 3.9 billion years. GA means billions of years here, near the boundary, really at the boundary between the Southern Highlands, shown in these warm colors, and the Northern Lowlands, shown in the cooler colors. And the crater itself is about 45 kilometers across. And the really cool thing about it, and the whole reason why we're there, is because it has this delta. This ellipse that you have here, this is where we knew we could put the rover down, somewhere in this area right here, near the front or edge of this delta. And a delta occurs when water flows into a standing body, or when water flows in a channel into a standing body of water. And you can see the channel that where the water flowed in. This is called Naret Navalis. And you can also see a channel where it flowed out. And so what that tells you is that at some point in Mars's history, again in that key time frame about 3.5 to 4 billion years ago, this crater was filled with water, maybe up to 100, even 200 meters depth. Here's an artist's impression of what that might have looked like, where you have water flowing in one side and then flowing out. And of course, you can already imagine, even if you're not a geologist, you can imagine that there are potentially habitable environments where life may have existed, either say in the margins of the lake, or even within the lake itself, or even the lake bottom. So where did we end up? Well, I showed you that ellipse before. Here's the front of that delta, and we ended up here. And this area in the center here, this is an area. This was a no-go for landing zone, and we can't even traverse across it. We've determined that since. So this is what's really great about that whole terrain relative navigation thing that I mentioned, is we're actually coming down and potentially landing in here, and it diverted laterally and ended up right here. And in fact, the strip that it landed in, the safe zone strip, is only about 200 meters wide. So it actually set down in this safe area. This landing site was later named Octavia E. Butler, after the African-American science fiction writer who was originally from Pasadena, California, where NASA JPL is located. So where have we been and what are we doing now? Well, this is the overview. We're in what's called the crater floor campaign, because we're on the floor of the crater. And here's the OEB landing site up here. This is a little bit busy, but I'll guide you through it. I'm going to show it again a few times because it is our map for what we've been up to. I've shown on here both the Perseverance path and Ingenuity's flight paths, and this is up to date. I downloaded this today. And as you can see, what we did is we actually decided to go south along this fairly good driving area. We couldn't go west because this area called Seta it's actually a Navajo word which means land of lots of rocks and sand, lots of sand, because there's lots of dunes that you can see in here, and it's very rugged. So this is this area that it diverted it and didn't land in. We decided to go around it and then toe dip into it in this area here. And in fact, we've just gone to our greatest extent within this area and are coming back out again. And this is where we are right now. So at the landing site, we landed, we started to look around. Here's one of the first images that was annotated and released to the public, where all we could really say at that point, we had no compositional information, it was just basically what we're looking at. And we have light colored rocks, darker rocks sticking up in the middle distance, regolith, which is the loose material, and some holy rocks here, and these rocks with holes in them continue to be intriguing. We've seen them a few times. They may be lavas that erupted with bubbles in them from the gas coming out of the magma. We've also done lots of other imaging, of course, as you can imagine. And this is a panorama that was taken from what's called the Van Zyl Overlook. This is where we sat for, I think it was several days at least, to support the first flight of Ingenuity. We had to make sure we were in a good location where there was good communication to support the first flight of the helicopter. But it's just great because you can continue, you can see that there's these flatter light colored rocks here and there's darker rocks that stick up. Of course, you can see the hills in the distance, as I mentioned before, are the rim of the crater. And then this flat sort of layer right here, you can trace along, that's the front of the delta. And I'll come back to this feature here. This butte over here is called Kodiak. It's part of the delta as well. But speaking of supporting Ingenuity and its accomplishments, it has outperformed itself many times over now. It was originally supposed to go for 30 days and fly up to 5 times at altitudes ranging from 3 to 5 meters for about 90 seconds each. It's far exceeded that. And I think we just finished flight 16 and the planned flight 17. This is from flight 3. And this is from 5 meters altitude, about 85 meters from the rover. And the great thing is you can see a couple things here. You can see the helicopter has a black and white camera that looks straight down, and it has a color camera that's basically like a cell phone camera that looks off at 45 degrees to the side. And that's what we're seeing here in this color image with these two ends of these 2 feet here. You can actually have actually been caught at the edges of this image. And if you look in the upper left there, we've actually picked up Perseverance. And here it is zoomed in. So here's the rover and then the landing site. And then you can see all the tracks that we've made since landing. So Ingenuity did these first few tests around and what's been christened Wright Brothers Field here near the landing site. With our support, it then basically went on ahead of us, as you can see, and it even flew across this area that we couldn't even dream about driving into. And the really great thing is that it's gone from being a tech demonstration into a reconnaissance mission. And a good example of that is from right here. This line right here, this is from flight number 12, where we commanded the Ingenuity to fly over the area that we intended to drive into, which is, as I mentioned, a tricky area because of the dunes and how rocky it is. And so it did that successfully. And this shows you a series of images that were taken that were later stitched together and actually incorporated into it. We have a GIS and everything for this, incorporated into that. But basically flying over the area that we've just spent the last several weeks exploring. And this is a completely a resolution and an angle of imagery that you would never get any other way than having a helicopter that could support you. So it's really kind of amazing. And where it's headed next is I think it's heading back out over, back here at the edge of Seta, and it's heading back out over the over Seta again. One thing I forgot to mention, just as kind of a guide to what we're talking about, is that's right. That's right. That's what I was going to say. So the reason why this is a Navajo word, Seta, is because we landed in the quadrangle that had been mapped before that was named Canyon de Chelly. And so Canyon de Chelly is within the Navajo Nation. It's a natural area in the southwest US. And we worked with the Navajo Nation to have suitable names for targets and features within this quadrangle. We then moved into Verdun, which is why you'll see French words come up as targets like Citadel and Brac and other things as we go along. So in case you're wondering why the names are the way they are, that's the reason. Okay, so the other thing that we'd be able to do is to use things like the Mastcam Z and the telescope on SuperCam to look at far off things, including Kodiak that I mentioned before. And there's a science paper that just came out on this a couple weeks ago on this Kodiak butte, just on what we see. And you can see there are flat-lying layers here. There's layers at an angle here as well. And if you look really closely in certain parts, there are boulders, and we could tell based on our resolution that some of those boulders are over a meter in size. And all of that allowed the sedimentologists, the sedimentary geologists on our team to provide additional constraints already on the conditions under which water was flowing into the crater. Even before we're still 2.5 kilometers away, even before we get to the delta. And that brings me back to the point that, you know, the river deltas are habitable environments. And so this is an example from Alaska where you have the river coming in, choked with sediment. It deposits the sediment. This builds out into the lake and into the subsurface. And you can imagine that there are different environments here that are habitable. But what does it take, even if we have these great instruments on the rover, including on the end of the arm, what does it take to actually demonstrate that that microbial life or its chemical biosignatures was actually present? What it takes is bringing samples back to throw everything we have at them in the labs on Earth at the samples. And so that's really where the core of the mission, we have this sample caching system. And the way it works is it cores a sample with this cylindrical part here on the end of the arm, and then processes it inside the belly of the rover. And I'll show you a video of that in a second. This is kind of showing you some early testing, but it has these two contact sensors here, these two posts. And then in the middle there, you can see there's a bit that's used for either abrading or coring. So to give you a sense of, actually, sorry, I'll go back to the map here so I can show you where we are. Okay, here's our first coring attempt here down. It took us a while to commission the coring mechanism system. And so we made our first coring attempt down here at what sort of nicknamed the thumb of SETA, right down here. So this is the spot that we chose. And in geology, generally, what you want is, if you're going to collect a sample, you want to have something that's representative. So you can see this is some of these flat sort of polygons or flat, lighter colored rocks. And these are everywhere. You can map them from orbit. You can say, you know, you can say that they characterize, and they've already been mapped as such, they characterize this geologic unit that we landed on and been roving on. So the idea was to get the first sample on this area, also because it's nice and flat. Engineers like that, right? Relatively safe. And so this is what we chose. And then this is actually showing you the first target, which is called Roubion. And you can see it's composed of this sort of polygonal area with these pavers inside. We nickname them pavers, like paving stones that you might have in your yard, landscaping. And you can see right here, there's an abrasion patch. And so the whole idea is that we have several types of bits that we can change out. But the first thing that we use and sort of the default is an abrasion bit. So it allows us to abrade the surface of the rock just to get rid of the dust and any layers of dust and other sort of material on top to get a look at the fresh rock. And then we can put the instruments, Sherlock and Pixel, on the end of the arm against that abraded patch and tell us something about the rock. And then right next to it, you can see here is a tailings pile from the Roubion sample attempt. So all of this is done autonomously. I'll show you the whole process, and everything worked beautifully for Roubion from an engineering perspective. So just let this run here. There may be sound that comes across, but it's basically just kind of machine whirring noises and things like that. So at this point, the coring bit is loaded inside here, as well as a sample tube. So it takes a sample tube and preloads that, so that as it cores into the rock, it's a rotary percussive drill. As it cores into the rock, this core, this little cylinder here, gets automatically inserted into the sample tube. Then it gets mated with the belly of the rover, and the sample tube then gets transferred into the belly of the rover. That's the yellow there. So that's the tube itself with the core inside. That gets grabbed by another robotic arm and taken over to a station where it's imaged. And there's a volume probe as well to see how full the tube ended up being. The image is called a cache cam. I'll talk about that. I'll show you pictures from that. And then it gets sealed up. So a cap gets put on it, gets hermetically sealed, and then it gets moved over to storage. Gets put back over in storage, actually, where the original tube was from. and then we drive off. And I'll tell you about what our plans are for the tubes later. So everything worked beautifully. Remember, we're not driving it with a joystick, so all the commands were uploaded to the rover the night before. The command was to go through this whole process that I just showed you schematically in the animation. Everything worked beautifully. We got excited, and then the cache cam images came down and the tube was empty. Nothing in it, like not even a speck of dust. So, and it was sealed as well. And so that had us scratching our heads, because the test bed that had been done for this had tested at JPL, had tested over 100 different types of rocks, basically anything that people could get their hands on from Southern California. Nice hard basalts to mudstones that are really friable. And every single time they got something inside the tube. So this was a real mystery. And then we started to look in more detail. Actually, it's kind of funny. We had a bunch of, I mean, it's funny, it's not funny. We had to spend a few extra sols. But some of the things we did included like using the Watson imager to look around on the ground, like look under the belly of the rover, like in case the core dropped out, like did we lose it somewhere? And didn't find anything. And so then we concluded that based on the properties of this rock, this is what's really intriguing about it. This is probably an igneous rock originally, but it's been soaked in water, and the alteration that has occurred along the boundaries of the crystals of the minerals in the rock has made it really friable. And so it basically pulverized, and the whole purpose of this thing is designed to move the tailings up and away to get solid material preferentially into the tube. So essentially the sample became loose material during the rotary percussive drilling, and then ended up in this pile of tailings right here. Now on the plus side, always look on the bright side, we have a hermetically sealed sample of Martian atmosphere in that. And I'm not just joking, because that's actually one of the samples that we want to have that comes back to the Earth eventually. So we've managed to do that with the sample. We just didn't get a rock inside. So with that, we then moved along, drove along the southern part of SETA, the edge, along what's called Artubi Ridge. We're headed back there actually in the next few days, up onto the ridge to get rocks that are stronger. The idea being, okay, we need an engineering win at this point, and so we chose this rock called Rochette, and you can see that it's kind of been wind eroded. It's sculpted by the wind. It's sitting up on this ridge here. It's actually almost in place in terms of where it came from. That's kind of important for geology, and but most importantly, it looks like it's strong, and sure enough, we did the first sample of this. We put another few commands in the loop as well to make sure that we had something in the tube before we sealed it up, including taking an image of the bottom of the tube, of the sample in the tube with the drill bit. That's what you see here. So that's really cool, because you can see the drill bit with the teeth and then the bottom of the core. And then we processed it, and there it is. And the sample is called Montagnier. It's in the tube. That's the cache cam image, and then there's the image after sealing it, hermetically sealing it. And this is actually the tube here, number 266, in the lab on Earth before it was loaded on the spacecraft. So that's the actual tube that it's in. So the first rock sample is in tube 266. It's now safely on board in the belly of the rover. With that success, we collected a second sample for reasons I'll explain, right from basically a few centimeters away, about 10 or 15 centimeters away. So we have another, basically a pair from the same rock, and this one's called Montagnac. And there it is in the tube and sealed up. So that's here at Citadel. So our first core attempt was there, and we drove along this ridge looking for a good spot to sample, and then we took these two cores right here at Citadel. And then we drove, and thanks to Ingenuity mapping, we went into SETA and to this far point right here, which is called Brac. And that's where we did two more samples of a different rock with different characteristics. Here is the target Brac. Here is the abrasion patch here. And then here is the first sample that we took, or the tailings pile from the first sample. And there's that sample that we took of the rock called Salette, and there it is in the tube. And it's different, has different characteristics, different mineralogy. There it is sealed up. But this is, and then we took another one from this, and it's called Coulette. So the pair for this one is Coulette. So that's 4, in case you're keeping track, that's 4 rock samples. They're pairs, 2 pairs, a sample atmosphere. And actually there's another one that's essentially a witness tube that's sort of like a blank that's meant to capture contamination on the spacecraft, which is technically the first sample that was taken. Why do I care about this? Well, it's not just because we want to, you can use these samples later to answer questions that we can't answer otherwise, but it's also because that's the whole, one of the whole reasons I'm on the mission in the first place. I applied, 3 years ago now to be a participating scientist. I responded to a call from NASA and then was selected as one of 10 scientists to be added to the mission to help advise the mission on exactly this, on what to sample, how to sample it, and then think about what questions we can answer with samples when they come back to the Earth. And what was really great about this experience, has been really great about this experience, is not only was I added to the team as one of these 10 scientists, but I was then asked to be on the what's called the Project Science Group, which is the leadership council for the whole mission as a representative of return sample science. So myself and my colleague Tanya from MIT are the 2 representatives of return sample science on the Project Science Group. It's exciting because, as you'll see, this is the first stage of bringing samples back from Mars. In my intro, as Amanda mentioned, I've been wanting to do this since I was about 13. I said I wanted to be there when the samples come back from Mars. That's been the goal of this guy right here. Okay, and then so we have plans. We have plans. We made plans before we landed. This shows you basically the geologic map that was made before we landed. Shows you the delta units in the blues, the crater floor units in the greens and tans, the crater rim in pink, and what's called marginal units are basically the edge of the lake kind of thing unit in this lighter colored green. And so we came up with ideas about, okay, if we land, here notionally just off the delta, which was the most likely place, where would we go, what would we do? Well, as you can see, we've landed over here on the other side of SATOP. And so the whole plan now is to we're headed right now in the next week, we'll be arriving, actually we're just about to arrive at another outcrop that we passed by on the way in that's of interest, that will help us sort of unravel the sequence of rock layers within the crater floor. And we're going to take another sample or pair of samples from there. And then after that, we're going to backtrack where we've just driven all the way around here on the good driving surfaces, and then start to head up onto the delta. This is Kodiak down here. I don't think we'll be able to visit it per se, but we'll be able to image it from this side. And then we'll of course be looking to sample other parts of the units within Jezero, including, say, on the delta. These are just some notional ideas, different phases of the delta rocks, this marginal deposit. And then the idea is that by the time we get to this near the edge of the crater rim at the end of the prime mission, which is in 3 Earth years from landing, we will have enough to put down an initial depot of sample tubes. Now, we don't expect that to be the end. So the whole idea, and this gets back to why we collect pairs of samples right now, is that we'll take one of the 2 pairs and put them down, one of the 2 pairs of each of the samples that we collected, and put those down in this initial depot, keep the other one on board, and continue on. Now, we may have to make some decisions. We won't necessarily be able to put duplicates of everything down, or pairs of everything down, but suffice to say, we'll put down, and this is, again, this is just schematic, but the whole idea is that we cache, in this initial depot, we cache representative samples of all the geologic units within Jezero crater. We carry then additional representative samples pairs of each of those with us outside of Jezero and continue to explore for at least another 3 years, another 1.5 Mars years. Continue to explore, and there it's an entirely new playground for geology-wise. Outside of the crater, we're into even older rocks, and that potentially have other environments that could have hosted life as well. So by the time we get to the next stage of Mars sample return, we will have 2 options. One will be this initial depot near the edge of the crater rim, and then the second one would be either on board the rover or we would have put it down at some later date. And then the whole purpose is to actually be able to bring the samples back. And this is where the follow-on missions are being developed as a partnership between NASA and the European Space Agency. So sometime around 2028, at least at the earliest, a fetch rover would gather up the samples from one of our 2 depots and deliver them to a lander, which would put them inside of a sort of oversized basketball-sized orbiting sample container with slots in it for up to, I think it's 30 samples could fit in there. There's 30 seats on that bus, and that gets blasted off the surface of Mars using a rocket. And then that orbiting sample container is captured by an orbiting vehicle that had been previously sent to Mars, and that would turn around and bring it back to the Earth at the earliest 2031. So it's ambitious, but we are essentially on the NASA Perseverance mission. We are at the front end of it, and our job, and that's why it's such an important component of the mission, is our job is to make sure that we get an absolutely compelling suite of samples that would really, so compelling that the space agencies could do nothing less than actually spending the additional funds to build these follow-on missions and bring those samples back, and provide samples like has been done with the Apollo samples for the moon that promise to revolutionize our understanding of not only of Mars, but of planetary geology generally and astrobiology as well. And so that's basically where we're at. And so you can follow along the mission shown in the lower right here. There's some absolutely amazing resources, as you can well imagine, for this mission. And all of the raw images, by the way, are fed to this website under images every single day as they get downlinked. So you can actually follow along in that regard as well. When you know there's a sampling event coming up, like in the next week, you can look to see if there are any cache cam images, because those are automatic, right? So little things like that, if you know how this thing works, and hopefully I've given you an idea, you can follow along. So with that, I'll end there, and I'm happy to take a few questions.
Thank you so much. That was very informative. I think a lot of people are going to be blown away right now and later on watching it again. So thank you so much. We have some questions coming from our YouTube live stream. So the first one is something like MOXIE being used on Earth for something like climate change?
Yeah, that's a good question. It's not, and the reason being that it's different from photosynthesis. What MOXIE does is it actually splits off an oxygen atom from CO2, so it produces carbon monoxide, and then it produces oxygen, which then recombines with other oxygen molecules to produce O2. So the products are O2 and carbon monoxide. In the Earth's atmosphere, if you did that, you just, out of the carbon monoxide, you just produce more CO2. So it doesn't actually, it doesn't help with that particular, with that problem of CO2 emissions.
Right.
Yeah.
Okay, great. Second question, why use a black and white camera instead of 2 color cameras on Ingenuity?
It's a cost thing. I think it was pretty low budget. I mean, that being said, it was $80 million for that little guy, but it is, yeah, even the the color camera, which is actually called the return to Earth camera. I forget the whole story there, but actually it's because they knew that if you put this color camera on the, like it was originally designed to have the black and white camera as the baseline, and that one is good because it allows you to do things like get the altitude and you know, as you're taking a sequence of images. But the return to Earth camera at an angle is the sort of the color one that's more flashy, and you know, it was, as you saw, was used to spot the rover at a distance and things like that. But it's actually the one that's also been used to do the mapping that I mentioned, the Recon that I mentioned.
All right, that's interesting. We have another question from one of our team members. Will you be receiving and analyzing the physical core samples in your lab facility, or will it be preserved somewhere else?
If only, yeah. No, the really intriguing thing and challenging thing, and didn't even go into it, is that for these types of samples, there's no facility today anywhere that could receive them yet. We have to design it from the ground up because a couple things. The number one reason is planetary protection. So if there are organisms that happen to be surviving, say at the bottom of the core or something like that, you know, protected from radiation, that sort of thing, we have to check them out to make sure that they're not dangerous and won't escape.
Yeah, absolutely.
And also we don't want to contaminate the samples with Earth organisms, microbes, which are everywhere, not to mention particles and all that kind of thing. And so there's no facility that allows you to do both of those. You know, you have BSL level 4 facilities, you know, where you study viruses and things like that, that prevent those potentially dangerous things from getting out, but that doesn't necessarily prevent other things from going in. So you actually almost have to have like a facility within a facility in order to really process these samples. So there's a whole other set of studies going on,
logistics, etc.
that are looking at what the sample receiving facility would need to be like. Now, the whole idea though is that once that's built and the samples are received in it, they're kept as a collection of samples, and then people like myself can write proposals and get a thin slice or pieces of samples
to get access to it.
Yeah,
absolutely.
And you know, I'm gonna have my favorites too by the end of this, having chosen some of them myself. So.
Yeah, no, it's great. I think it's we're at the point where we're developing infrastructure for this, right? So it's basically from now until the end of time. So and then I guess on another note, so we've had technical questions. If I were to ask you more of a research question, what goes into planning a mission like this? So what is, let's say, some of the milestones that you had to set? And how long does it take to plan a mission like this?
Well, I'll answer the second one first. It takes years and years to plan a mission of this magnitude. And the instruments that I showed that are on board were competed. So NASA put the call out. They said, we're building a rover. And if you sort of recognize the rover, it's like Curiosity, which has been going for 10 years almost, but with a different set of instruments on board. And so they competed those, so the instrument teams joined. So there was a lot of that planning that went into play. And then in the last, prior to landing, we did the planning that I alluded to, where we were mapping out sort of potential traverses and potential sample suites that we might collect and that sort of thing. So there's a lot of that, that type of thing that goes on as well. And then of course, when you land and, you know, the reality is different, then you modify and replan.
Great. Thank you. We have another question from our member, Michael.
Yeah, thank you for the presentation, Dr. Hurd. My question was, so you mentioned that you need the samples to actually make some kind of assessment of whether there's life or was life in Mars. I'm wondering, what are some of the roster of tests that are confirmed, or I guess even in planning for, you know, when these samples, you know, hopefully when they come to Earth, you know, in the next several years?
That's a great question, and I meant to look it up. There's a paper that came out in the last month that has a series of life detection criteria that's been proposed by some authors. So I'm not completely up to date, but it's things such as, microscopic fossils, although those are really difficult to actually say for sure, because there's lots of other things that could look like microbial fossils. But a lot of it has to do with chemical signatures. So metabolism, and for life as we know it, will fractionate, will change ratios that exist naturally of elemental ratios, or more likely isotopic ratios of things like carbon or hydrogen. So there are things like that that we need to look at. And then there's also the presence of particular organic molecules that would be an indication that life was there, from the breakdown of cells or as a product of metabolism, that sort of thing. I should have mentioned that Sherlock on the end of the arm is able to detect organic matter through fluorescence. So but that's also, again, it's a triage thing. It allows us to sort of say, hey, this is a sample that would be worth, or sorry, this is a rock that would be worth sampling because we see hints of organic matter in it, based on that in situ analysis. But to really tease out all of these things that I mentioned, that's why we have to have it back in labs on the Earth. I think it was Carl Sagan that said that extraordinary claims require extraordinary evidence. And so that extraordinary claim that life was there in Jezero Crater Lake 3.5 billion years ago, that has to be backed up by a whole series of tests and evidence and peer review that says, yeah, there is actually something living here at that time.
I guess it would also strengthen the claim if multiple samples had similar signatures, or at least there was some consistency across. So you're not just doing duplicate, but maybe triplicate and stuff like that.
Yeah, absolutely. That's an excellent point too. And even the rocks that we've looked at so far, I kind of alluded to it, that we've sampled that are in the bag, as we say, they may be igneous, most likely igneous rocks, maybe lava flows or something similar, but they've got this alteration signature of water. Now, we don't know if that was at the bottom of the lake or when that was or how that was, but the point is that water has flowed through these rocks and made changes to the mineralogy. So even that, even though it's not like a mudstone at the bottom of or as part of the delta, which would be I'd say you could argue an even better target, and certainly one that we have in mind, or at the margin, right? That environment at the edge of the ancient lake, those are really strong targets. But yes, absolutely. If you go to those places where the environment looks really conducive to life living and being preserved, but you also do those tests in the igneous rocks that have alteration, yeah, absolutely. That's part of that entire process.
That was a great question. That was really informative. So on that note, we will wrap up. We are at the 1 hour mark. However, this was a very